Well, welcome everybody. My name is Paul Habets. I'm a Director of Marketing and Sales at Fibrant. And I have a few topics for you today. A little bit of chemistry. Don't be afraid, it's just the basics. And I have an overview of the Polyamide 6 market and what choices you can make as a designer, as an engineer, as an owner of a company, or of a strategic position within the automotive industry. So a little bit about the background of our company. Fibrant is since a few years part of the Hyson Group. The Hyson Group is a privately owned multinational with a 6.5 billion euro turnover, and it's the world's largest producer of caprolactam at Polyamide 6 yarns. Caprolactam is and it's the bit of chemistry I have for you today. It's the building block of Polyamide 6. Polyamide 6 nylon is one of the most used engineering plastics in the automotive industry. So together with the Hyson Group, we have a total production capacity annually of 1.3 megatons of caprolactam, which is roughly 15% of the total world production. And being with that, with these numbers, we are right away world's largest producer of this particular product. It also brings quite some responsibility with us, which makes sure that we need to sustain quality, and also I need to make sure that sustainability is very well defined within our company. A little bit of history to understand where we are coming from is that since the 50s, we are already producing caprolactam in the south of the Netherlands, being part of DSM at that point in time. Already in the mid-50s, we already had sustainability high on our agenda. At that time, we already had depolymerization activities where we brought back polymerized polyamide 6 back to its precursor, back to caprolactam. And the same we did in a larger scale in 2000 in the US, where we transformed polyamide 6 based carpets back to caprolactam. In the US, the carpet industry is relatively large. Many domestic and offices, hotels have a lot of carpets, which is a very nice source of product to bring back in a circular way to the same industry. In the 2010, 2012, we went into more and more bio-based caprolactam. One of the technologies which we have developed in Geleen was a patented process in which you can use sugar fermentation to make bio-based caprolactam. This is still a very innovative way of producing caprolactam out of sugars and enzymes and bacteria. But it's still very small. It's still in a laboratory scale at this point in time. Currently, in these times, we are focusing more and more on full circular products based on pyrolysis-based products, which I will share a few more details with you later, and bio-based with bio-feedstock-based caprolactam, which can be used as bio-based polyamide 6. Also for that, I have a few examples later on in this presentation. As mentioned earlier, technology is very dear and near in our heart. We really believe that by understanding technology, by inventing new technologies, you can make major steps. And that's also why we are located on the bright side, in the Camelot side in Geleen, because that's really a hub where innovation is brought to practice. And also they delivered a few technologies which we already take into practice already today. So our HPO technology, the technology to produce caprolactam with a limited amount of side products. And these side products, obviously, now the less side products you make, the less burden you have on the environment. And our latest innovation, which was even on the news, is that we have invested significantly in N2O abatement. So N2O is a gas which is produced during the production of caprolactam, and we installed a technology and we invented technology which ensures that the N2O is completely taken away from the process, which resulted in a carbon footprint which is a record low of 3.3 kilograms CO2 per kilogram caprolactam produced. Well, where is all this product used and in which countries? So just to give you a little bit of a view on the polyamide, on the caprolactam market, you see on the left-hand side, you see our consumption per region. And what's already peculiar is that the Asia is one of the largest consumers of caprolactam. And the main reason for that is that the textile production is obviously a very high consumer of polyamides. Think about the nylon stockings, underwear. Think of all the outdoor equipment, outdoor ropes, which are out there. The majority, certainly if you go to the higher class and higher quality products, are all based on polyamide 6. If you look to the compound business, the engineering plastics part, the majority is automotive. The harsh environments, the robustness of the products, the temperature ranges applications have to go through, the quality which is needed, well, points in many cases to polyamide 6, and that's where polyamide 6 is used the best. So in this way, today we are roughly 106.2 megatons of caprolactam is produced every year, which translate in a multitude of this in compounds polyamide 6. So yeah, as you can imagine, after all these years, almost 70-80 years of nylons, yeah, it has proven its performance. And on the right-hand side of this slide, you see a multitude of applications, and there are much more of these, which are used in today's cars, in combustion engine cars, but also in cars which are electric hybrids, or which are fully electric and hydrogen powered. One typical character is always that, well, temperature performance, impact resistance, versatility, high quality. If that's needed, normally the weapon of choice is in many cases polyamides, and polyamide 6 is one of the materials which is used the most. So when creating a product, unfortunately, in every step which we have in the chain, from fossil fuels up to waste, CO2 is produced. And I think in today's time, in today's environment, we have to make sure that we do this in a smart way, and that we reduce the CO2 production to an absolute minimum. Actually, that we try to prevent CO2 produced by itself. So it is a responsibility in the value chain that we make the right choices, and that we make the clever choices, so that we have not only a sustainable and suitable product for today, but also for tomorrow. In this presentation, I will focus on the caprolactam and polyamide 6 production processes, and the choices you have today and you will have in the future. But obviously, by creating a design, and Luc already named a few examples in the complexity of making designs, there are many choices to make. So, and it's not only about integral costs, it's not only about quality, but also sustainability is an important factor as well. You need to design to make things circular. You need to design to make things more unimaterial. You need to make designs to have a lowest possible impact on the environment. And that's of course something which is the trade of the designers. And what I would like to do in this presentation is to give you a tool set and an information package to make these choices. So the engineer's dilemma. Well, you made a beautiful design. You made the choice is polyamide 6. And then what? Are you then ready? Is this then the choice? Any given polyamide 6 works? Unfortunately, the answer is not that simple. So if you look to the next slide, and this is some data which I got from Plastics Europe, one of the most pronounced agencies in Europe. You see that the European average caprolactam impact, and European is including all the Russian production sites, which is round about roughly between 20 production sites, we have an average of 6.4 kilograms CO2 produced per kilogram caprolactam. So if you make from 1 kilogram caprolactam 1 kilogram polyamide 6, you have to add 0.3 kilograms of CO2. So 1 kilogram PA6 means 6.7 kilograms average kilogram CO2 per kilogram polyamide 6. So with all the investments which we have done, we are now currently the benchmark in Europe when it comes to carbon footprinting. And this you can already see in this graph. In 2021 is the year in which we are reducing ecolactam. You see that we have a carbon footprint which is 3.3, which is extremely low. But that's not it. So we are not stopping here. We have a complete roadmap in place in which we are introducing new technologies, new energy streams, new feedstocks to ensure that we keep on reducing our footprint to zero, which is our ambition before 2040. So that was the traditional oil-based chain. Obviously, there are also other ways to make a positive contribution to the system, to your environment, and to bring sustainability higher on the agenda. One of the streams we believe in is the use of bio-based precursors and bio-based technology. I already mentioned the innovations which we have looked into sugar fermentation and to bring that to a next level. Unfortunately, with the developments which we have done today, we see that ramping up this to a scalable size, it's relatively brings its own challenges. We believe more that if we want to make a quick step, and if we want to reduce carbon footprint and introduce bio-based precursors fast, we have to look into really bio-based feedstock. And then you have two choices. One choice is to have bio-based crop and plant-based feedstock, or you use biocircular waste, which is actually the waste of plants. We took a deliberate choice to not choose bio-based product. I think it's in this environment where you have a growing population around the globe, where still food is extremely important, and will even get more important, is that you need to have food is to feed people, is to feed animals. The waste from harvest and the waste from wood, for instance, that's a beautiful product you can use, and there are technologies which are allowing that. And one of the technologies which we are currently using is to use wood waste from the paper industry and wood waste from harvesting, to pyrolyze this back to tall oil. And tall oil is a precursor which can be fed into crackers, and in these crackers you can make benzene. Benzene is used to make phenol. Phenol can be used to make caprolactam, and the circle is round. The interesting thing is that if you use this kind of feed stream, is that you can even reduce even further your carbon footprint. If you look at the green bars, and I plotted them against our current blue bars, which is the oil-based caprolactam, you see in comparison to the European average that you have a significant reduction. So you see that with the technology which we are currently have in-house, which is the state-of-the-art production technology for caprolactam, you can go to a carbon footprint of 1.5 kilograms CO2 produced per kilogram caprolactam, which means that if you translate that into polyamide 6, you would have a polyamide 6 and neat polyamide 6 with a carbon footprint of 1.7, 1.8 kilogram per kilogram PA6, and is extremely low. There are other ways to contribute to a better footprint and to a more sustainable environment. And let's look at depletion of resources. You know that resources are very scarce, and actually, if you look at it, burning fuels to propel cars is actually a very inefficient way of using your feed streams, because once your fuel is burned, yeah, you cannot use it anymore. So circular ways of looking into reusing your oil is obviously very favorable. And by transforming oil into plastics and making it circular is, of course, a very nice way to keep value in a circular chain. And there are several ways to do that. And the nice thing about polyamide 6 is that this product is extremely versatile. You can use waste, you can use neat waste, which you can mechanically recycle back to polyamide 6. This is already done today. You can buy a recycled polyamide 6, very good quality. Unfortunately, with every turn you mechanically recycle your polyamide 6, you deteriorate your quality. And that's not an infinite gain. So there is a certain point of time that you deteriorate your quality to such a level that it's very difficult to use in high performance parts like you would have liked to do that for the automotive industry. The other way is to look at depolymerization, to bring polyamide 6 back to its precursor, back to caprolactam, back to its monomer. And that's a technology which is already used today, which has been used in the past, but it needs a relatively pure stream as well. So the more pollutants you have in your product, the less efficient your depolymerization process will be. So that's also why design for circularity is extremely important. So in some cases, if you will use this technology, it's very important to ensure that you have your feed stream secured, so that you make sure that the designers also take care about the fact that their product is a 100% polyamide based product, or is very easy to disassemble, to ensure that you have a feedstock which can be used over and over again. Another more generic way of looking at circularity is chemical recycling and pyrolysis. So at this point in time, and also on the Camelot campus in Geleen, there are several initiatives in which you see that pyrolysis ovens are installed. So what do these ovens do? They take in an enormous amount of a mixed plastic and bring that back to a naphtha-like product. That naphtha-like product, it can be fed into naphtha crackers again, and these crackers bring it back again to all kinds of precursors, including benzene. From benzene you can make phenol. Phenol can be used to make caprolactam, and we are back in business again. So that's a way of bringing plastic waste back to its original shape and form again. And this can be done numerous times without any loss of quality. The material is chemically 100% identical with its earlier shape, so there's no deterioration in quality whatsoever. So depolymerization and chemical recycling are very interesting technologies which have a huge potential to make value chains circular again. So actually, that's one of the last slides I have for you. Basically, the choice is yours. So there are several ways to look at it. If your choice is polyamide 6 for your product, please take away from this presentation that polyamide 6 is not just polyamide 6 if you look from a sustainability point of view. So depending from which kind of source you buy from, you already see that you have a difference of, well, 6 to 7, maybe even to 8 kilograms per kilogram product produced. So it can have a huge impact in your performance. Circularity is already available. Bio-based products are already available. And if you can use mechanically recycled product, please do so, because if you look into the carbon footprint and if the performance allows, it's a very, very interesting way to reuse your product and to make your product even more sustainable. That's the last slide I have for you. If there are any questions, please let me know. Thank you for your attention.